All right, we've been discussing the Fourier transform, and I think we've done a pretty good job at just looking at the waveform and what is A not equal, what is omega not equal, or what is the period. All right. And we might have done a few simple examples just to verify that we're using the math right. So we did sine omega t, a DC, and we might have talked about the pulse a little bit. Oh, okay. I thought you were fixing something, Devin. All right. No worries. All right. Now I talked a little bit about the project. Where we're going to take a pulse and we want to turn that into a DC. All right. And this is an everlasting signal, meaning it's always doing this pulse shape, right? It's not strictly true. It will change on us, okay? When we want half the supply voltage, we'll be at 50%. If we want less than half, then we'll reduce the time on period. Right? If we want more, we'll try to get more, right? So what the microcontroller will be changing is how long is it on, all right? And another term for that is duty cycle. And that equals 100 times tau divided by T naught. And in the book, tau is the time that it's on, and A is how high it is. All right. And so one of the homeworks, we ask you to derive that out. Now, yeah, in the homework, they want you to do this. And today we're going where this is centered at 0. So this is even, so you'll get some kind of cosine, all right? But you can delay this or accelerate it so that we can get where it starts at 0, goes up to 1 at time equals 0, the way I've drawn it. And so we'll do this example, which then should be able to help you derive it out. Now, yeah, the book has the answer. And so you should be able to check your work and make sure you're getting the right thing. No, I'm not going to draw this 50% duty cycle like I normally do. And a lot of times, industry will just say 50% duty cycle, 100% duty cycle, 79% duty cycle. And you can derive it in those terms as well. But just to look, we'll just, tell how long signal is non-zero, and everything else, like the period, the amplitude, should be pretty straightforward. Now, the very first thing we need to calculate is A naught. And that is 1 divided by the period, right? We're going to integrate over the period, xt dt, right? But just by looking at it, right, if this was on 100% of the time, well, the average would just be A, right? If it was on half the time, the average would be half A. If it was on 1/4% of the time, it'd be 1/4%, right? So we already know that this, average should be A something like this, right? That when tau is equal to T naught, that's 1, and then we get A. So it should give us something like that. All right, as we just work our way out. So what is this function? Well, it's just A when it's high, and it's 0 when it's not. So I don't really have to integrate anywhere else except from 0 to how long it's on, right? So that gives me my A over the period part, my 0 to tau part, and then if I integrate a constant, I'll get T. And so this is the part we want for the project, is that we are converting this pulse width to a DC. Now, you can still output sine waves and triangle waves. It's just at any moment in time, the pulse width is fixed and you're getting an average. But this can change in time. The pulse width, this, right, we can make a function in time. And as long as it's a lot smaller, well, I'll show you where it'll work and where it won't. So it can be a function of time, right? Because just like a music player or your smartphone, right, it's using pulse width modulated on your speaker, that changes in time. But we're just, to analyze each particular part, we're keeping that fixed in time. So like I said, that's the bit we want in this particular project, right? The rest we're trying to get rid of, but we need to calculate it anyway. So let's find AN when it's greater than 0, right? We already have A naught, but let's use the formula. Equals 2 over T naught. Right, we're going to integrate over the period. What is our signal? Okay, and the A's, we integrate over the cosines. All righty. We're not going over the whole period because it's only non-zero between 0 and tau. And in that point, it's A, right? And then the cosine n 2 pi t. We get that. And so here we have this, and we just have to evaluate it. In this case, sine at 0, it's always 0, right? And so then what we're left with is one over n pi. So the higher order it is, the lower the amplitude is going to be, right? Then we have sine n 2 pi tau divided by T naught. And, you know, tau divided by T naught times 100 is the duty cycle. All right. So now all I have to do is know what is how long am I on, what is the period, and then what harmonic I'm going for, and I can calculate AN. Right. And maybe just as a quick refresher, because sometimes you get really into the math and you forget what it is you're doing, but, you know, Fourier series right? We break up a periodic everlasting signals into DC plus the sum of cosines and sines. All right? That's what we're trying to do. We've got the DC part, right? Even though the coefficient is given in terms of sine, right? The ANs are really associated with the cosine part. All right. So we just did the cosine part. Now let's finish off with this, the sine part. So it's the same as before, except now we're going to integrate over with a sine wave. All right. But we still get we only have to integrate up to tau again. All right. So I kind of jumped a step. No, not really. So we're left with still the same coefficient, right? I don't know. Where did it go? In my when I was working it out, I had set A to 1. Sorry about that. Thanks. So cosine of 0 is always 1. But then when you multiply it through, we can keep this here and just have 1 minus cosine. All right. Now in the book, they did it so I'm saying I did this, right? The book did this. Okay. And you can see that's got more of a cosine type shape. This has more of a sine type shape, at least the way I've drawn it. All right. So I just did this in Excel where I have n, right? Here's, we can call T naught. I call this T for tau. I guess I can call it tau. All right. Calculated AN. Calculated what BN would be. All right. So if n equals 0, BN, it doesn't exist, or you can just put a 0. And notice tau is 0.1. So 0.1 divided by 1, right, is 0.1. So that is our coefficient. So if I change that tau, how long you're on, to half, right, it goes to a half. If I change it to 0.75, it goes to 0.75. If I change it to 0.25, it goes there. So let's talk about 0.5. All right. So the ANs deal with the cosines, right? And the BNs deal with the sines. At 50% duty cycle, we've talked about how that looks very close to a sine wave, right? And so the way I've drawn it, starting at 0 at time equals 0, going up to 1, right? Rather than having it split across 0. And so you get these, yeah, are they non-zero? Well, that's really just an artifact of the calculations. In this particular example, if one coefficient is a half and the other ones are something to the minus 17, these ANs are effectively 0. All right. And then if we look at the BNs, right, so omega 1 is the first harmonic. So if it was 1 hertz, right, that's a period of 1 second. And that means the first sine wave has an amplitude of 0.63, right? And it doesn't matter if I'm using a kilohertz square wave, right? That kilohertz, the first harmonic at a kilohertz will still have that same here. And the reason why I just used 1 second and tau is because tau is equal to the duty cycle, the percent, not the percent duty cycle, but the fraction of the duty cycle. And you can see that the magnitude, the 0.5, that's what we want. But this is the first harmonic. We don't want that. But then interestingly enough, not everything, this goes to 0. Then it's actually only the odds have harmonics. All right. And then to plot it out in the C notation, okay, that's really just magnitude and phase. So you have the magnitude, you know, something squared plus something squared, take the square root of it. And then the phase, it's a little trickier. You just have to follow the book. All right. But the thing is when the magnitude is so small, a phase of 180 doesn't really mean anything. But you can just see that everything is the phase 90, phase 90, phase 90, phase 90, right? And so if I wanted to try to recreate that, a square wave, I would put in the DC amount, 0.5, plus this magnitude times the sine wave with n equals to 1, and then I would add in a phase of minus 90, right? And then I would just keep adding them up from there. All right. That can be a bit messy doing it like this, so I'm going to let that be. But you can anyway, here's the magnitude. That's the signal we want. This is just n. So it's just n times whatever the frequency is on this axis. And then everything over here we'd want to filter out, right? So if I want this and want to get rid of everything else, that's why it's a low pass filter. Now, if I was trying to create a sine wave, well, maybe I would just want this, right? And I would use a band pass and get rid of the DC and then try to get rid of all of these, right? And if I wanted, I'm not quite sure what I would call it, I could do a high pass where I would sum these and get rid of that. But really, we're trying to get this signal at n equals 0 or a frequency, you know, a DC. So this is the bit we want. That's the bit we don't want. Now, there is something interesting that happens is when they start talking about the like when the signal doesn't repeat. So if I have the signals on for a tenth compared to being the period of 1, you actually start to see this sync function. That's not a big deal for today, but I just thought it was interesting when I noticed it. All right. I'm sorry. I'm having a hard time here. I have to trick it. So I'm just going to call this signal 1. And I'm going to make it a pulse. It's going to go from 0 to 1. I'm going to put in super fast rise and fall times. And I'm going to put in T on at 0.5 and a period of 1. And then just simulate for 2. All right, so there should be my pulse. All right. Let's call this A naught. And A naught was just really the duty cycle times the magnitude. So that's really just 0.5. All right. So we run. And so this is our approximation to that square wave with only A naught, right? So either it's missing half, even it's half too low or half too high. So I think we need more of a series to represent that. So for 50% duty cycle, the ANs, right, canceled out. I mean, we're 0. So then I'm going to go for the BNs. The first BN that is non-zero is in fact when n equals 1, and it's 0.64. Or I'm going to go for the magnitude, all right? And that's, yeah, we'll just use 0.64. So I'll call this signal B1. We'll make it a sine wave. No offset, amplitude 0.64. Frequency was 1 hertz, right? Yeah, 1 hertz. Now the delay it was giving as minus 90. I'm not too sure about that. No, I don't like that. So what I'm doing here is I'm just going off of BNs. I'm not using magnitude and phase because I just not trusting that. So BNs are all sines, right? With no phase. The next one is B3. And that's 0.21. So that's 0.21. Now the frequency, n is 3, so it should be 3 times the 1 hertz, so it should give me 3. Okay. Oops. Okay, it's getting better, right? Isn't that a little bit better? Closer? Please say yes. The next one is be 5.13, we'll call it. Point 0.13, 5 hertz. All right. Now, it's getting closer, right? But you can see that you might be imagining to yourself, it's going to be really hard to get a square corner here, a 90-degree corner. And you can't get back the square wave by summing an infinite sum of these. And you might say, well, you just don't have enough time. If you had enough time, if you had infinite time, you could add infinite sources with infinite computers and infinite LT spice, and you should be able to do it. But you would find before that is that the errors in the calculation would prevent you from achieving it. All right. What are the errors in a computer is that even with a 64-bit machine and double precision numbers, right, you have about 13 digits of precision, and then you have your exponent. And so that 14th digit, what is it? You don't know. And so that's like a digitization error. And so that'll prevent it. And you say, well, hey, I'm going to go downstairs and I'm going to get all the function generators I can. Those are analog. And I'm going to hook it up. And, you know, it might be, I know how to make a summer with an op amp, and I'm just going to sum all these signals. But the problem is that in analog signals, even though we kind of say, oh, it can be infinite levels, but the noise causes errors. And it's actually really hard to show, but if you look up Gibbs energy, it'll show you that you can't do it. But the thing is making a pulse out of sine waves isn't really what it's about, right? I'm showing you this to show how, yeah, the more I add, the closer I get to my original wave, right? And the book has other examples too, like a triangle wave and things like that. But the real key is that I can represent them mathematically that way, and I know where they're going to occur, and I can filter them or multiply them or do whatever I want to do to them as I go. And yeah, in the back of today's notes, it's a rather lengthy derivation, and I'm not going to show it because it's something better just to read. All right, but the Fourier series of a pulse train, which is the term they use in the book, has, you know, DC plus sines and cosines. All right. Now the thing is there was only sines when it was 50% duty cycle. When there was different percent duty cycles, you had sines and cosines. All right. But these sines and cosines are really just a ripple, right? And in a DAC, it's just error. Okay? We don't want it. So we want the A tau here, right? We don't want sines, cosines, ripple, error, whatever you want to call it. Filter. Okay. Now we're getting into a little bit of the project right now. All right. And I think I have to just maybe review a little bit of digital, right? But let's just say I have a 2-bit system, right? That's 0, 0. You know, if I'm coding it like this, right? I have these values, right? So, right, I can be here, 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 or here, right? 1, 2, 3, 4 states, 1, 2, 3, 4 states. So if I have a sine wave, or if I just have a wave, right? If it's digitized, right? Well, let's say if it's below 1, it's going to be 0, right? Then above 1, it's going to be 1. Then above 2, it's going to be 2. And here it's going to be 3, right? That's all I can get. All right. And this is kind of going the other way, analog to digital. We're going from digital to analog, right? So this space, right? It's like it's our resolution, all right? So let's just take a 1-bit system, all right? I'm changing my mind. I'm expanding this. All right. That this is my output, right? Is that as long as it stays in here, it's not gonna be greater than 1, right? And as soon as it goes over, right, then it'll be 1. Now, we've talked about this signal, right, at 50%. We'll have this, it'll be flat, and then it'll have all these parts to it, right? And even though right, we can do a filter that, yeah, it's attenuating all of these, they're still there. So you get the 50%, but you're getting this ripple, all right? The ripple is uncertainty. So yeah, here I am here, and if I go to 10% duty cycle, I'll move down here, and if I go to 50%, 75, I'll go up here, right? But there's always this ripple that I have to deal with. And that ripple, right, where in this case, right, anything in here was a 0, anything up here was a 1. But now is, well, how tight can I get these levels together? Well, I don't know what these ripples are going to be. I mean, I kind of can predict them, but it's like really an uncertainty. And so the V peak to peak of the ripple is min resolution. All right. So if my V peak to peak ripple after filtering, let's say, is 0.1 volt, and my and I go from 0 to 5, right? So I have 5 volts, I have 0 volts, right? How many levels do I have? Well, I can only go in increments of 0.1, right? So I'd have 5 divided by 0.1. So I have 50 levels, right? It can be 50 levels. If I try to make my levels smaller, right, if I have a ripple here, right, that means I have to have, non-overlapping ripples. But if I try to have overlapping ripples, well, I just really won't know where I'm at, okay? So that ripple is your minimum resolution. And then you just do log of 50 divided by log of 2. And that gives you your effective bits. And that's how you can get fractional bits, right? Oh, because it's base 2. The question was, where does that log 2 come from? I guess I could have written log to the base of 2, 50, but I always forget how to code that, so I just divide it by the log of 2. All right. And these are in the notes from today. But I thought I thought it was possible to break it down just a little bit. Now here's the thing. Is that 50% duty cycle has the max ripple, right? Or lowest resolution, okay? It means all you got to do is test at 50% duty cycle. And you find the worst case ripple, which is the worst case resolution, which is the worst case effective bits. You don't have to test anything else. You are done for characterizing. I mean, there's more tests to run, but in other kinds of analog to digital, in other digital to analog converters, right? If you have an 8-bit converter, right, you've got 2 to the 8th tests to run. If you have a 16-bit converter, you have 2 to the 16th tests to run. For the PWM converter, no matter how many bits, you've only got 1 test for that particular thing, right? Now, yeah, you probably have to run some other tests just to make sure your microcontroller is programmed properly. All right. So that's the thing. Testing is a huge part of the budget. Sometimes it's easier to design it than to actually verify that it worked. So if you can reduce your test budget, you're making the product for cheaper, right? So through Fourier series analysis, you can prove that's the case. Therefore, you know what's going on. Also, the fact, yeah, just that there is this spectrum and you're trying to grab a part of it, right? That's another key. But the other thing is, when you do a step response, or let's do a pulse, all right? And let's just say it's a kilohertz pulse, right? And I put that into an op amp, right? I have my various models. Right, that I can get some mighty strange behavior due to the gain bandwidth, due to the fact, right, that we've got these models. And you might say, oh, well, let's say my gain bandwidth is 10 megahertz. Hey, this signal's only a kilohertz. Well, a kilohertz is a lot less than 10 megahertz, right? You'd think you don't have to worry about it. But, right, 1 kilohertz will put, you know, at n equals 1, you're going to get a 1 kilohertz. Then it's going by odds. Let's say it's 50%. Then it's 3 kilohertz, 5, right, so on. And so, yeah, these get smaller as time goes on. And yeah, by increasing by 2, it's going to take many signals to get up to here, right? So we can even sorry for those thing just popped out. Okay, so yeah, that is kind of, that's 10,000, right? All right, at 10,000, V naught is much less than 0, much less than 1. It's very small, right, compared. So yeah, that particular, right, because here we're out at 28, or let's say 27, right? You can see that the amplitudes are getting smaller and smaller and smaller. So that's 1, and you're 10,000 times bigger, you can see that it's going to get really small, right? But if you're saying, hey, I'm at 100 kilohertz clock, right, and I got a 1 megahertz gain bandwidth, well, this signal, yeah, even though it's smaller than the gain bandwidth, you think you're okay. No, these infinite sums are there whether you like it or not, okay? And so I think I've tried to say that with the gain bandwidth, right, I'll say, hey, stay here, right? That's the safe place. But a step function, but a pulse, which is 2 step functions, right, makes it so you can't stay in the safe zone. There's going to be signals out here, an infinite amount. All right. So testing with, even though testing with steps, and what do I, or pulses, well, because a function generator, right, you don't really get a step function, you get a pulse. You can just make this super long where it looks like a step function, right? But it's always going off and on, right? When we test like that, we're going to get these higher order frequencies, even though we might not be near the gain bandwidth. All right. Knowing why that is another reason why we studied the series. I know that was maybe a lot. Are there any questions? I just have to look at the green sheet in the 110 lab. So the question was, hey, when are we starting this project? Well, let's see. Green sheet. Yeah. All right. So the other question was, give me a heart attack. Is there an exam next Wednesday? No. No. So yeah, the final project are the last 3 lab sessions, and so you would start it on the 20th, right? And really, you've got but you haven't really worked with the Fourier transform in lab yet. But now I've introduced it. Now it should make sense. You've done filters. You've synthesized the notch filter. You've done transfer functions. You know Bode plots. You now have almost all, at least in lecture now, right? You've got all the components to come up with it. So next time we have control theory. All right. So we've got 2 control theories, and then stabilization. It's just the way the book is then they have gain bandwidth kind of tucked in at the end of a later chapter where this screen sheet I probably just need to change, because really what's left before this midterm are the control theory parts and the fact of converting a mass spring damper circuit into an RLC circuit. Some of these modules, yeah, it depends how much time I have to show you the other examples. Where's the... Yeah. Anyway. So the Fourier series, right? Sum of sine and cosine, right? Which really can be cosine omega t plus a phase, right? Well, the thing is that's really just like the phasor, right? Where we had one volt at 90 degrees, and what wasn't shown is frequency equals 1 hertz, right? So all of those right, this right here is ultimately just the magnitude. This bit's the magnitude times the sine wave, and this part here is just the magnitude times the cosine wave. So magnitude, you have a sinusoid, and that gives you either, in the A and B, there's no phase, right? When you combine it into one, where you have the magnitude of both of A and B, then you get a phase. So really, back in 98, right, you learned phasors. But the Fourier series is just take a signal and break it up into phasors. That's it, right? Now, and I even noticed I had made a mistake. I think I corrected it, where sometimes I'll confuse Fourier series and Fourier transform. All right. Now, really, the Fourier transform is just this. Okay. Laplace is all right. So the thing about the Fourier series, sum of cosines and sines, right? The assumption is that those sines are everlasting. Even the DC signal never changes since before time began till since time never ends. It's always that way. And the thing about an everlasting sine wave is it's almost the same thing. It's always been a sine wave, and it's never ever going to change. Yes, it changes in time, but the fact that it's a sine wave never changes in time. So the Fourier series acts on those kinds of signals. The Fourier transform, well, the way they derive it is that you can do it for everlasting, but you can also, like if I have a pulse, right, this looks like an everlasting signal. But what if my pulse is thin, it's only on, right? And let's say it takes infinity time for it to turn back on again. Well, in fact, now we're back to the step up, step down function, right? But notice j omega t. Here, the Laplace transform, everything is zero. You can have initial conditions, and then things can change. But they're not everlasting. Okay? Now, right, this is the imaginary axis. This is the real, right? Laplace can have poles and zeros, right, all over the place, right? But where does the Fourier transform come from? Well, it's just this axis, j omega, right? So how do I, so if I take the magnitude of my transfer function, right, and the phase, right, and plot it on the Bodhi, right, S equals j omega. So we're really plotting along this axis, and these are there, right? They're affecting HS, right? But we're only plotting this axis. So a zero will depress this signal, and it'll depress it. So this will be lower. A zero goes to infinity. A zero goes to infinity. I'm sorry. The x is the pole. That's 1 over 0 at that point, right? So this is going to infinity, right? This is going to infinity. So it's going to raise this up. Now I'm actually trying to work on a better way of thinking about it, but let's just say I put a blanket here, right? And I put a pole here. That's like, you know, somebody under the blanket pulling it up to infinity. So the blanket, the covers are coming up here, and the Bodhi plot will kind of have this shape. Or that's the frequency plot. The Bodhi plot would look like that. But you have minus frequency and plus frequency. All right. Right. If I put a 0, it's like somebody pushing the blanket down, and so this gets pushed down. All right. So when you push and pull, yeah, you can get the this kind of thing, which is a high pass. It's not, that explanation isn't quite ready for prime time. Okay. But it took me a while to figure out why he never showed Bodhi plots and why the filters came so late in a section called Fourier. And that's because really S equals j omega, well, that is the Fourier transform, right? But these poles and zeros on Laplace can be converted into that by taking the magnitude and phase. And then what we're going to go over is something called stability. And that poles over here and poles here will cause things to be unstable. All right. And I just, so if you looked at if you remember the 101 with those RLC circuits, right? What did we talk about? Over, under, critical. But all the roots were in the left half plane, right? Well, if I make R minus, I can actually kind of have signals that go to infinity, but they can kind of be an overdamped infinity, underdamped infinity, and a critical infinity. So there's in fact 6 things that could happen. One, we did tell you, one was the 3 were there, right? Over, under, critical, plus some made up thing it was never that. And then sometimes R was negative, which then made one of these uncontrollable things. And so that's what we're going to do next time, is take an uncontrollable system and make it controllable. And yeah, if I'm balancing this mass, right, and it gets a little bit off center, right, the more it goes, the more it goes, the more it goes, until It falls down. That's positive feedback. So if you put a control system of a cart, how can you make it stable, right? So this look under inverted pendulum in the book. All right, now I know you got to go, so I'll just let you go. Sorry for giving you extra.